Welcome to qnawire.
Hi everyone, so what we have is a submarine that has a total ballast tank volume equal to 700 cubic meters. It is initially only filled to 100 cubic meters with air at 1500 kPa and 15 degrees C. Additional air at 1500 kPa and 20 degrees C is pumped into the tank until it is full, and during this process we also have seawater that is leaving the tank at 15 degrees Celsius. What we're asked to find is the final temperature and the mass of air in the tank. So the first thing we're going to do is state our assumptions. We're first going to assume that air is an ideal gas with variable specific heats. We're also going to assume that the process is adiabatic because that's given to us, and we're also going to assume that work is also zero. Next, we're going to write down the properties of our gas air and some properties of the water. So since we know we're dealing with air, our gas constant is going to be 0.287 kPa cubic meters all over kilogram Kelvin. Our specific heat ratio of air is going to be 1.4, and our specific volume of water will be 0.001 kilograms per meters cubed. Meters cubed per kilogram. Next, what we're going to do is we're going to go ahead and apply the conservation of mass principle to air. So we know that the rate of change dma dt of air is going to be equal to m in, because that is our air, that is the mass that is coming into our system, and that's going to be m in. Similarly, our dm water over dt is going to be minus m out, because that is leaving our system. Now what we can do is we can combine this with internal energy and enthalpies to say that 0 is equal to d mu of air dt minus or plus d mu w of dt plus hw, the m dot, the mass flow rate of water, minus the enthalpy of air times the mass flow rate of air. Now we're going to combine this with the conservation of mass expressions, and we'll actually be able to cancel the dt terms. So what we're left with is d mu air plus d mu water is equal to h a dma minus plus hw dmw. Now what we can do is integrate this entire equation from the beginning of the process to the end of the process, and what that gives us is mu of 2 minus mu of 1, all for the air, plus mu2 minus mu1, all for the water, is equal to enthalpy of air m2 minus m1 of air plus enthalpy of water m2 minus m1 of the water. Now what we can do is substitute the ideal gas equation and the specific heats into these expressions and expand. So what we can do is we can write this as PV2 over RT2 CVT2 minus PV1 all over RT1 CVT1 minus MW, 1 CW TW, and this is all going to be equal to CP T in PV2 all over RT2 minus PV1 all over RT1 minus MW1 CW TW. Now what we can do is we can just solve for T2, and we'll see that the expression for C2 is T2 is equal to volume 2 all over V1 over T1 plus 1 over K T in V2 minus V1. And after plugging in for all of these terms, we get a final temperature equal to 386.8 Kelvin. So that's the final temperature in the tank. Remember, we're also asked to solve for the final mass in the tank as well. So what we can do is we can just use the ideal gas law and say that M2 is equal to PV2 over RT2. And for plugging in these terms, we see that the final mass is 9,460 kilograms. And that's our final answer.